Today is our second lecture on game tree search. In the last class, we talked about two-player games and how we can formulate it as a search problem. Today we will have the second part of this lecture. In this lecture, the student will learn how the search tree for two-player games can be pruned using alpha-beta pruning. In the previous class, we looked at Minimax search for computing the best move for a player. But Minimax is quite inefficient, and we will see how Minimax search can be pruned using alpha-beta cutoff values. Given a search tree, the student is expected to be able to apply alpha-beta pruning on the search tree and show which are the nodes which will be expanded and the nodes which will be pruned. The student will understand what is the optimal saving by using alpha-beta pruning for a game tree and what is the minimum amount of pruning that can be obtained. They will also be familiar with certain strategies used in game tree search, like the quiescence effect, the horizon effect, transposition table, endgame database, etc. So, to recollect, we have considered two-player perfect information zero-sum games where we have two players, min and max. And the full min-max tree can be drawn so that the terminal positions are either a win, draw or loss, and we can assign a value, a payoff value to the terminal position. When generating the entire tree is not possible, we saw that we can decide to cut off search at a particular depth, at a particular level, and use a static evaluation function at the terminal nodes. Thus, the tree, the game tree that we generate, the leaves are given a definite score. In the last class, we saw how the Minimax algorithm defines how the scores are backed up from the leaf towards the root. So, that is what we studied in the previous class. Now, to briefly recollect, a game tree is like a search tree. The nodes are the search states. The edges between the nodes correspond to moves. Leaf nodes correspond to determined positions. And at each node, it is one or the other player's turn to move. Now, the problem with Minimax is that Minimax is extremely inefficient. That is, Minimax expands all the nodes in the given search tree. That is, if we start from the root and search p ply or d ply up to a depth of d, and assuming that this game tree has a uniform branching factor of b, then the number of nodes expanded or explored by Minimax is b to the power d. So, Minimax will expand b to the power d nodes in order to compute the Minimax value of at the root if it decides to cut off search at depth d. However, note that while we are doing this Minimax search, we are only concerned with the best move for max at the root level, the best move at the root level. We really do not need to have the correct minimax value at all the intermediate nodes. The exact minimax value we don't need to have for all the nodes. So, we really just need to know the minimax value at the root node, or rather we want to know which is the best move at the root node. So, if we consider this, we show that we can devise an algorithm which expands less nodes than Minimax does. Now, let us, before we go to the formal properties of the algorithm, we will take up an example and show why such pruning is necessary or such pruning can be done. So, let us consider this game tree. The square node correspond to the max player and the round nodes correspond to the min player. Here it is the max player's turn to move. At this level it is the min player's turn to move, and at the lowest level here again we have the evaluation for the max player. Now, you see, suppose, so the minimax values can be computed by depth first search. So, suppose this leaf gets evaluated first and it has a value of 3. Now, when this leaf is evaluated, the value of the min node must be 3 or less than 3, because min will compute the min of all the children values. So, the value of the min node can be 3 or less than 3. When the second node is evaluated, we know the exact minimax value of this min node, which is equal to 3. Now, when the minimax value of this node is equal to 3, since this is a maximizing node, the value of this node must be greater than 3. The min of this node is exactly equal to 3. So, the value of this max node must be greater than 3, because max is a maximizing node. It has already found a path through which the minimax value is 3. It can try another path. It should go to another path if its minimax value is greater than 3. Okay. So, when we come here, we know that the max value must be greater than 3. Now, we come and explore this node. Now, at this node, max has a value of 2. Now, if max has a value of 2, the value of min at this node must be less than 2. Okay. But if the value of min is less than 2, max has already a path where the value of minimax is 3. Along this path, the value of minimax is less than 2. So, max, whatever be the actual payoff values at these nodes, max will not be interested in this path. Okay. For example, even if the value at this node is equal to, let us say, 100. Okay. Suppose the value is equal to 100, even then max will not be interested in this path, because in that case min value will be still less than 2. If the value here is, let us say, minus 1, the min value will be equal to minus 1. So, the min value at this node can be less than 2, cannot be greater than 2. Therefore, the values of these nodes are not important for max, because max knows that this is a path with a better guarantee. So, max need not compute these nodes. So, search can be cut off at these two paths. So, this is the idea of the pruning that we will talk about today. So, what we do is that we start propagating the costs as soon as the leaf nodes are generated. We do not explore nodes which are guaranteed not to affect the choice of the move using minimax search. So, we want to prune the search tree so that we still get the same strategy as we would get by full minimax search, but we avoid expanding those nodes which do not have any effect on deciding the correct move for max. So, this strategy of a pruning is called alpha beta pruning. So, alpha beta pruning is some type of branch and bound pruning, and the idea is that we cut off search when we cannot do better than the best so far. To implement alpha beta pruning, we associate with the nodes the alpha and beta values are associated with the nodes. Usually, alpha is meaningful for max nodes and beta for min nodes. So, we can keep alpha beta values at all the nodes, and alpha value of a min node could be the alpha value of its max ancestor, and beta value of a max node is the beta value of its min ancestor. So, at every node we store these alpha and beta values. At a max node, we will store an alpha value. The alpha value at the max node is a lower bound on the exact minimax score of that node. So, initially we can initialize the alpha value of all max nodes to be minus infinity. At any intermediate point, the alpha value of the node is a lower bound on its actual minimax value. So, alpha value of a node can only increase, right. So, if a max node has an alpha value equal to alpha, its true value might be greater than or equal to alpha. Now, if we know that min can choose moves with scores less than alpha, then min will never choose to let max go to a node where the score will be alpha or more. So, let us just look at a diagram to explain what this is about. Suppose this is a min node. Now, suppose min has a path whose minimax value is known to be, let us say, equal to 7. Now, suppose min has another path to a max node whose alpha value is equal to 10, which means that its minimax value is greater than or equal to 10. Now, since min is a minimizing node, min knows that this path is better than, min knows that this path is better than this path, because in this path the actual value is going to be greater than or equal to 10. So, search can be pruned at this path. Okay. Similarly, the beta values can also be used for another type of cutoff. At a min node, the beta value happens to be a lower bound on the exact minimax. At a min node, the beta value is actually an upper bound to the exact minimax score. At a max node, the alpha value is a lower bound. At a min node, the beta value is an upper bound. So, the true value might be less than equal to beta, because beta value is an upper bound. Now, if we know that max can choose moves with score greater than beta, then max will never choose to let min go to a node where the score will be beta or less. Let us again draw a diagram. Suppose this is a max node. Now, suppose at this min node, max has a path whose minimax value is known to be equal to, so let us say 10, and there is another path So, there is a min successor whose beta value is equal to 7. Since the beta value is an upper bound, the actual value of this node is less than equal to 7. Because max is a maximizing node, max will always prefer this path to this path. So, this path need not be explored any further. So, this is the sense of beta cutoff. Now, why can we cut off search? Let us consider this example. Wait. Let us consider this example. In this example, at this node, the terminal value is equal to 3. At this node, the value is equal to 5. So, when this 3 is discovered, min gets a beta value of 3. That is, the value of min will be greater than equal to 3. When this node is found, then beta value remains 3 and the value of min is now exactly equal to 3. Because the value of min is exactly equal to 3, we can set the alpha value of this node equal to 3. Okay. Therefore, max value will be less than equal to 3. Now, search comes to this node. This node has a value equal to 2. So, because this node has a value equal to 2, the beta value of this min node is set to be equal to 2 and actual value of min is less than equal to 2. Okay. Now, since beta value is 2 here and the actual value is 3 here, max will never consider going along this path. So, this path can be, rest of this path can be pruned off, which means that these nodes need not be explored. Okay. And the optimum path for max is along this path, and for min here it is along this path. Now, if the alpha value at a max node is equal to alpha, means that max can guarantee a score of at least alpha if he plays judiciously at that point. If the beta value of a min node is equal to beta, it means min will guarantee a score no more than beta if he plays judiciously. Okay. So, this is the essence of alpha beta cutoff. More generally speaking, at max nodes, if an ancestor min at, suppose we have a max node, right? If there is an ancestor min node whose beta is less than alpha, then this node is irrelevant. So, the ancestor need not be the exact predecessor, it could be some other ancestor. So, just to draw a diagram, suppose this is a ancestor, this is a max ancestor, and then there is some parts of the tree and there is a min predecessor. Now, if this max ancestor has a alpha value of equal to alpha, and if this node has a beta value of equal to beta, and if beta happens to be less than alpha, then max will never consider a move through this point. So, below this node, the rest of the node expansions can be cut off. So, if a min node has a beta value which is smaller than alpha value of one of its max node ancestors, then search can be cut off at this node, because a path through this node would be irrelevant for max, because he has already found a path with a guarantee of at least alpha. Okay. So there are two types of pruning that can be done, one from the point of view of max, the other from the point of view of min. So search can be discontinued at a node under two circumstances. Number one, if the node is a max node and the alpha value of this node is greater than equal to the beta value of any min node ancestor. This is called beta cutoff. The other case which we just discussed is if we have a min node and its beta value is smaller than the alpha value of any of its max ancestor, then also search can be cut off. This is called alpha cutoff. Okay. Now, how to compute these alpha beta values? We will outline an algorithm for computing the alpha beta values. The computations of these alpha beta values will be very similar to the minimax computations, and they can be done in a depth first manner. So, however, while computing the alpha beta values, we need not explore all the nodes of the search tree. And as a result of this computation, we get a final backed-up value at the nodes, right? Some nodes we do not explore. For them we do not care about the value. For those nodes where we do find a backed-up value, that backed-up value may be the exact minimax value, or it may not be the exact minimax value. So the backed-up value is either the exact minimax value of the node, or it is an approximate value, and the alpha value of the max node is a lower bound on the actual minimax value. The beta value of a min node is an upper bound on the actual minimax value. And as I mentioned, we do not really need to know the exact minimax values to compute the best strategy for the max. Okay. Now, let us see how we can calculate the alpha values at a max node. What we do is, we first, when we are at a max node, we first evaluate the value of one of its successors. If the exact value of one of its successors is known, then let me just draw a diagram. Suppose this is a max node, and suppose this max node has these three min children. So when the exact value of the first child is computed, suppose the value of this first child is -1. Then, so initially the alpha value of this max node is let us say -infinity. When this node is fully evaluated and its exact value equal to -1, we set the alpha value to be -1. Okay. Then we evaluate the value, the beta value of this min node, right? Now, or rather, when we find the value of this min node, if its value is, let us say, 3, then the alpha value is updated to 3. If the value of this node is -2, because -2 is less than 3, the alpha value stays as it is. When all the children of the max node has been evaluated, its value is, the alpha value is the exact value. But before that, we can say that the alpha value is a lower bound on the exact minimax value. So instead of, so this happens when all the nodes have been fully evaluated, but even if one of its successors have not been fully evaluated, but a beta cutoff has occurred, we can terminate search at that point and find out the final backed-up value at the max node as its current alpha value when we finish dealing with all its children or when a beta cutoff occurs at this node. Similarly and symmetrically, we can compute the beta value at min node. After we obtain the final backed-up value of the first child of a min node, we set beta of the node to the value of this first child. When we get the final backed-up value of the second child, we decrease beta, update beta if the new value is smaller. When we have the value of the final child, or if alpha cutoff occurs somewhere, then the beta value becomes, so if the alpha cutoff occurs at this node, then the beta value becomes the final backed-up value of this node. Now, you see, the question that we have to ask is, how effective is alpha beta pruning? How many nodes does it prune? So, before we answer this question, let us trace alpha beta pruning over a slightly larger tree and see how it works, and then we will discuss how many nodes are pruned under different circumstances. So, this happens to be the schematic diagram of a game tree where the leaf nodes have been assigned certain values. Now, you see, when depth first reversal occurs, first this leftmost leaf will be evaluated. His value is equal to 4. Therefore, the beta value of this min node is equal to 4, that is, the value of this min node is less than 4. Okay. Now, after 5 this node is evaluated, the value of this min node will be equal to 4. So, initially the value at this min node is less than 4. When this is evaluated, the value at this min node is equal to 4. Now, if the value at this node is equal to 4, the alpha value at this max node will be greater than 4. So, we will put here greater than 4. Okay. Now, this child will be evaluated, and to evaluate this child will be evaluated. When this value is evaluated, the value of this min node will be greater than 3, sorry, less than 3, it is not greater than equal to. So, this is less than equal to 3. When this node is evaluated, this value will become equal to 2. The final value will be equal to 2. And if the final value is equal to 2, the final value of here will be equal to 4. Okay. So, if this value is equal to 4, the beta value of the min node will be equal to 4. That is, the value of this min node is less than 4. Okay. Now, this child is going to be evaluated. To evaluate this child, to evaluate this child. So, this node gets a beta value of 6. After this node is evaluated, the final value of this node is equal to 6. Now, the alpha value of this max node will be equal to 6, that is, the value of this max node is greater than 6. Now, you see, let us look at this min ancestor. The value of this node is equal to 4. The value of this node is greater than 6. So, this node does not need to look at this path. This path is clearly better than this path. So, search can be pruned at this point. Okay. And the backed-up value here will be equal to 4. Now, since the backed-up value of here this is equal to 4, the alpha value of max will be equal equal to 4, that is the value of max is greater than equal to 4. Now this child, therefore this child, therefore this child, therefore this node will be evaluated. The beta value here will be 1, and after this is evaluated, the beta value, the actual value will be equal to 1. And then the alpha value of this node will be equal to 1. Okay. Now, let us come to this child. This child, we evaluate this. So, the beta value of this node is equal to 2. So, this node can improve further. So, this is better than this. So, we evaluate this node and the actual value is equal to 2. Therefore, the max will actually get a value of 2. Now, let us just look at this. This min node now will have a beta value of equal to 2. So, the actual value is less than equal to 2. Now, look at this max node. It has one child whose value is equal to 4 and this child has a beta value of 2, that is, its actual value is less than equal to 2. So, max need not consider this path, and this will be the best strategy for max at this point, and therefore, search can be cut off at these points. So, these nodes need not be evaluated. Okay. So, this is the minimax values of the nodes, but if we do alpha beta pruning, this is how the nodes are evaluated. And as we can see that these nodes were cut off by alpha beta pruning, they were not evaluated, and also this portion of the tree, they need not be evaluated when we use alpha beta pruning. And this shows the same diagram. Now, so here we have some deep pruning at the right half of the tree. Now, let us try to outline the entire minimax search. So, we assume that minimax is done at the max node and maximin is done at a max node and minimax is done at a min node. And let us assume that Vn is the static evaluation of node n. Now, we outline the algorithm for maximin and minimax. So, maximin is done at a max node. So, maximin takes as argument n, the node, the alpha value and the beta value, the current alpha and beta values. So, if n is at the search depth, we have reached a leaf, then we return the v of n. Otherwise, for each child m of n, so each child of max will be a min node. Its value will be computed by recursively computing minimax m alpha beta. Now, if this value returned is greater than alpha, then we set alpha equal to value. So, we look at one child, it returns a value. If the value is greater than the current alpha value of this max node, we update the value of alpha. Now, if the current alpha value happens to be greater than equal to beta, where beta is the value of its min ancestor which has been propagated to this node, in that case we will return alpha, because we need not explore this max node any further. Okay. So, this is the computation done at the max node. We start at a max node, we find all its min successors, we expand the min successors one by one, we take the first successor, find its minimax value, and if that value is greater than the current value of alpha, alpha is updated, and as a result, if alpha becomes greater than equal to beta, then alpha value is returned, otherwise we continue until all the children have been solved. and the alpha value has been obtained, and this alpha value is returned by the procedure maxi-min. At a min node, we do minimax, which is just a symmetrical function. Minimax of a min node again takes alpha and beta. So, beta is the beta value of this node, alpha is the alpha value of its max ancestor or max parent. So, if n is a leaf node, we return v of n. Then otherwise, for each max child of n, we find value of that child by calling recursively maxi-min. If the value returned is less than beta, we update the beta value of this node. Now, if this beta value happens to be less than equal to the alpha value of its max ancestor, then we return the beta value. So, there is a mistake here. So, we return the current beta value, and then we cut off search at this point, otherwise at the end of this loop we return the beta value. So, this is minimax. Now, let us look at the performance of alpha beta. So, if you see, when we have a tree whose branching factor is b and its depth is d, we have seen that the number of nodes in this tree is of order b to the power d. It has been shown by Noth that in the best case, the number of nodes expanded by alpha beta pruning will be equal to, so best or minimum number of nodes expanded or explode by alpha beta is order b to the power d by 2, which is square root of order b to the power d. Okay. And the best case occurs when the best child is always the first one which is explored for at every node. Okay. In this case, when the best child is the leftmost child and that is explored first, we get the correct value in the beginning, and in that case the number of nodes expanded is smallest, and it happens to be the square root of what would be expanded by minimax search. The worst case, not surprisingly, occurs when the worst child is always the first one to be expanded and the best child is the last one to be expanded at every node. In that case, alpha beta pruning would not have any extra savings over minimax, and all the nodes expanded by minimax would be explored. So, the number of nodes expanded is between order b to the power d by 2 and order b to the power d if you use alpha beta pruning. In practice, for a random ordering of the nodes, you do the average number of nodes pruned is quite significant to make alpha beta pruning very attractive. However, okay, I'm not getting the slide. So, however, we can improve our chance of achieving better pruning by doing move ordering. That is, you see, we do not know when we start with the search, we do not know which child is better. But if we use the static evaluation function of the children to order the to decide the order in which the children expanded, we can expect for a good evaluation function that a minimax or with alpha beta pruning will expand many more nodes, expand less nodes and prune more nodes. So, the efficiency of alpha beta depends on the order in which the nodes are encountered at the search frontier. The optimal number of nodes expanded is order b to the power d by 2. So, this happens if the largest child of a max node is generated first and the smallest child of a min node is generated first. In the worst case, the complexity is order b to the power d. And if we assume a random ordering, then the number of nodes expanded is order b to the power 3/4 d. Okay, which actually means that if due to our resource limitations, we can, if you use minimax search, we can go down to a depth of d. That is, if we can do a d-ply search with minimax, we would be able to do a 4d by 3 search, 4d by 3 ply search using minimax, assuming random node ordering. And if assuming very good node ordering, we can search to twice the depth, and that would often lead us to have a much better strategy. So, minimax does improve the depth to which search can proceed due to pruning the number of nodes that need to be expanded. Additionally, a number of improvements have been developed to improve performance with the limited computation. So, we will briefly discuss some of the other issues that people have come up with for game trees. So, as I already mentioned, by using node ordering, using the static evaluation function or the current value, etc., we can get close to order b to the power d by 2. So, the effective branching factor would become root b. So, node ordering, instead of generating the tree left to right, we reordered the tree based on the static evaluations at the interior nodes. Okay. So, at every node, we look at the children, we apply static evaluation on the children, and according to the value of the static evaluation, we order the nodes. Another idea, when we have limited resources available, so another idea is to do iterative deepening search. So, initially we do a search up to 1 ply and we get a possible value, a particular best suggested best move. Then if we have time, we do a 2 ply search and update our best move. Then we do a 3 ply search, then 4 ply search, then 5 ply search, then 6 ply search, and so on. When the time is over, when there is no more time left, we use the best move as given by the previous iteration. So, we use iterative deepening and we use time. When time runs out, the move recommended by the last completed iteration is made. Iterative deepening can be combined with node ordering to improve pruning efficiency. Instead of using the heuristic value, we can also use the backed up value from the previous iteration at the nodes. So, that is another idea that one could do, which can improve the pruning in certain growth tree. There are two other points. In a game tree with fixed cutoff depth, there are often some problems which people have noticed. One of these problems deals with the concept of quiescence. Quiescence happens when a play has settled down, and if you go down that search tree further, it is unlikely that the evaluation function would change much. So, if we can recognize in the game tree that at a node it has reached a quiescent position, we need not waste our effort in expanding that search frontier further, and we can concentrate our efforts in other parts of the search tree which are more likely to change the evaluation function as we go down. So, this effect is called the quiescence. Secondly, often in game tree search we notice the horizon effect. So, horizon effect happens when there is a particular set of moves, so that there will be a dramatic change when a particular move is taken, but you can use stalling operations to stall the inevitable bad or good position. So, one in the game playing situation, one can stall for time. So, they can postpone the inevitable win or inevitable damaging move by the opponent over the horizon. So, that if we stop search at a particular point, we might get an evaluation function which is dramatically different from what would happen if a move is taken to take care of that stalling. So, what is the solution? So, when people write game programs for quiescent search, so instead of cutting off the search at a fixed depth, the good game playing programs, they evaluate those positions which need to be explored further, because you expect a change in the backed up values if you explore the search tree, and there are some positions whose value is sort of closed, unlikely to change when you explore the tree further. So, if you can detect these quiescent positions, you can terminate search at those points. So, you have a variable depth search tree. The horizon problem is not so easy to handle, and there is no general solution. So, some heuristics could be used for some specific games. Then there are certain other strategies that people have employed. For example, sometimes transposition tables are used. So, some game trees or game graphs are more graphical in nature, that is, there are many repeated positions. So, for efficiency, it is important to detect when a state has already been searched. In order to detect a search state, previously generated game states with their min-max values are stored. You see, this sort of transposition tables will be important if you look at the game of NIM. So, in NIM there are many repeated states. So, it makes sense to store, if a node has been solved, it makes sense to store the state along with the backed up value obtained there to avoid repeated exploring of the same node. Then in many games, the opening and the closing situation need very careful attention, whether it be a game of chess or the game of backgammon, which is of course a game of chance. So, you see, most board games, they start at the same initial position, and then there are a set of best moves that you can take from the initial position. So, instead of using Minimax or alpha beta with alpha beta to find the best move, it makes sense to generate a table of good initial moves in consultation with a game expert, human expert, and this is known as the opening book. So, opening book can be used. Then as end game is another interesting place where there is a lot of expertise required. So, a database of end game moves will be very helpful. So, a technique for calculating end game databases is also helpful. Then for playing more sophisticated games, one needs special purpose hardware. For example, the chess games. you can generate more number of moves per second if you have special purpose hardware. So the best machines today are based on special purpose hardware designed and built to play specific games. And then, as I already mentioned, do selective search. The motivation is that humans are competitive because they know humans do not, when humans play games, they do not look at all possibilities because they are not equipped to do that. So they are very good at selecting those promising possibilities. So selective search will identify the promising possibilities and search only on the interesting portion. And we get best first minimax, which I will not discuss now. So to end today's lecture, I will end with a set of questions. And before I come to the question number 1, I will just define the game of MP-NIM. MP-NIM is a stones game where we have or a matches game. There are P piles of M matches in each pile. To move, a player will remove any number of matches from exactly one pile, and the winning player is the one who removes the final match. This is the game of MP-NIM. So the first question for this lecture asks you to consider the game of 2-2-NIM. That is, you start with 2 piles, each containing 2 matches. So you have to draw the game tree, part A. Part B, you mark on this tree the values at the terminal nodes. The terminal nodes will have a value of +1 if it is a win for max, -1 if it is a win for min. Question C, apply minimax on this game tree and mark on the tree the packed up value on the root node and use these values to find the best starting move for max. Part D, can max force a win in this game? Part E, find out if alpha beta pruning on this tree gives rise to pruning some parts of this particular search tree. Okay. Then question number 2, you are given this game tree. You are going to apply minimax with alpha beta pruning on this game tree and identify the best possible move for max. Very simple game tree. Now, if we have time, we will discuss briefly the 2 questions that we had for on lecture 7. Question number 1 for lecture 7 was, suppose the game tree for a particular problem has a branching factor of b. If you do a p-ply look ahead and then apply minimax on this game tree, how many nodes will you expand per move? So this is actually quite easy. You have a tree whose branching factor is b and the tree is to the depth of p-ply. So this is p-ply. So for every move, you need to do a p-ply full minimax search where b to the power d nodes are expanded. For each move, you need to expand b to the power d nodes. Question number 2, it actually should be 2, not 1. Consider minimax search on a game tree with p-ply search and another minimax search on the same game tree with a q-ply search. If q is larger than p, which of these searches is guaranteed to find a better strategy for the max player? So the question is that if we do a p-ply search and find the best move in those situations, and we do a q-ply search and then again find the best move, so find the minimax value, which of these searches gives rise to a better strategy? The answer is, we normally think that a q-ply search is better than a p-ply search if q is larger than p. And the intuition is that we think that if we go deeper down the tree, we will have more accurate evaluation functions as we are nearer to the terminal positions. So, if we are at a terminal position, then we know the correct value of a node. And we assume that if we are nearer to the terminal position, we have a better estimate of the correct value. So, we expect that a q-ply search, the leaves evaluated, for these leaves we will have a better estimate, and based on these evaluations, when you do minimax, we find we might find a better strategy than what we would find in a search having p-plies. However, there is no guarantees here. So, we cannot guarantee that a q-ply search will be larger than a p-ply search, even though we expect a q-ply search to be better. So, the answer is none of them are, it is not guaranteed that one of them will be better than the other, even though the q-ply search is expected to be better than the p-ply search. With this, we end today's lecture. Thank you.